Greetings A-level chemists, welcome to a little explainer video which is all to do with catalysis and catalysts. So let's start by explaining or describing what a catalyst is. So a catalyst increases the rate of a chemical reaction without being used up. How does it do this? Well, catalysts provide an alternative pathway for the reaction, and this alternative route has a lower activation energy. Okay, so catalysts provide an alternative pathway for the reaction with a lower activation energy, which we are going to call EA. Capital E for energy, subscript lowercase a for activation. Now, catalysts don't affect delta G, delta H, or delta S, but they do affect the activation energy, EA. When we're looking at equilibria, catalysts speed up both the rate of the forward reaction and the reverse reaction, but they have no effect on the position of equilibria. Okay, so it's just worth getting this down. So catalysts do not affect, so they have no effect on the position of equilibria. Okay, so do not alter the position of equilibrium reactions, but they increase the rate of the forward and reverse reactions. Okay, so just to go through point 2 in a little bit more detail, what we're going to do is we're going to plot an enthalpy profile diagram. So we all remember this from GCSE and from some year 1 chemistry. So on the vertical we have enthalpy. So let's put enthalpy. Let's label the vertical as enthalpy, and on the horizontal we've got progress of a reaction. So let's just say that our reactants have this level of enthalpy, and if those are our reactants, where do our products go? Let's just do it for an exothermic reaction. So our product's going to be lower in energy, so they're going to be more stable. So let's say our products are here, and let's label those guys as my product. Okay, so then we don't just go straight away from the reactants to the products. Okay, that doesn't just happen. We have to surpass this hill or this barrier, and this barrier is called the activation energy, which is used to break up the bonds and get the reaction going. So we've got this hump to surpass, and let's do it in green. So we've got a hump that looks like this for an exothermic reaction. And then what we're going to do is label some terms. So let's start by labeling the activation barrier. So from the reactants, from the endpoint of the reactants to the top of the hill, that is my activation energy. Let's move it over a bit. So that is my activation barrier, or activation energy, EA. And that is energy that we're putting in to break the bonds in the reactants, and then they rearrange the atoms, forming new chemicals, i.e. products. So that is the pathway, and we can think about this as riding a bike or driving a car. So let's say we've got a little Fiat Cinquecento or something. It's a bit old, it's a bit of a banger, and we're driving along and we encounter this large hill, and we know that the Fiat Cinquecento isn't going to get up it because we have to go quite high up in energy and the car just can't manage it. Okay, it's a bit of a dud car. However, imagine if there was an alternative route to get from A to B, rather than going up this hill. Well, it just so happens in this magical fantasy land that there is a tunnel which is cut through. And because there is a tunnel that has been cut through this hill, that means I don't have to go up in energy. I don't have to put stress on my car. What I can do is, because there's a tunnel that's been cut through, I can drive straight through rather than going up in energy to go from A to B. And this alternative pathway has a lower energy requirement, and that's what a catalyst does. It provides an alternative route, and the alternative route has a lower energy requirement, therefore increases the rate of reaction, because we don't need particles with this much energy colliding, therefore leading to successful collisions. We can lower the energy requirement for a given reaction. Okay, so going away from cars and going back to the chemical domain, let's have a look at how the energy profile diagram looks for a catalyzed reaction. Well, we're going to have a lower energy requirement, so the hill isn't going to be as large. So our activation energy this time is here. We've got lower activation energy, and that is EA cat. So that's EA, but this is a catalyzed reaction now, okay? So I'm just going to label that as EA cat. And while we're here, let's just finish it and make it complete. That the difference in enthalpy between the reactants and the product is delta H. And in this case, delta H is a negative. So this is delta H. And in this case is negative. So therefore exothermic. Now, doing a little bit more year one revision, we can also have a look at the distribution of energies in a molecule. So we can tie this in with Maxwell-Boltzmann distributions. So if we label these axes, so here is my energy value X, and this is our frequency number of molecules with energy X. So 0 molecules have 0 energy. Okay, so it starts here, and let's say this is our distribution of molecular energies. Something, oh, that was terrible, so we'll try again. Something that looks like this. That'll do. Okay, that's satisfying enough, and that's at a particular temperature. So that's our distribution of molecular energies. So let's say that the activation energy for a given reaction is here. So let's say that is our activation energy. There it is. And what we're saying here is we interpret that as the area under the curve. So the area to the right of that energy value illustrates the number of molecules. So if we integrate that, that's the number of molecules that have energy greater than or equal to the activation energy. Okay, so this is the number of molecules, or the fraction of molecules with energy greater than or equal to the activation energy. And by adding a catalyst, remember, we're lowering the energy barrier. So if we're lowering the energy barrier, the activation energy, we're going to move left on the energy axis. Agreed? So therefore, this is the energy requirement for the alternative route. So we're going to label that as EA cat. And if we label that as EA cat, look at what we've done. We don't just have these molecules, which have the energy which is greater than or equal to the activation energy. We have this fraction as well. So we have A and B. So now what we have is a larger fraction of molecules. We have a larger fraction of molecules with the energy which is greater than or equal to the activation energy. So therefore, when they collide, it results in a successful collision, and therefore more molecules have that energy. So there are going to be more frequent collisions, therefore the rate increases. So let's just get this down. So a larger fraction of molecules have energy which is greater than or equal to the activation energy, therefore more frequent, successful, collisions. And there you go, that was a quick run through of some year 1 kinetics. Okay, and let's just put a box around that to make it a bit more neat and manageable. Okay, so now we're going to delve into some heterogeneous catalysis. Okay, so there are 2 different types of catalysis that we need to know about. One is heterogeneous catalysis and the other is homogeneous catalysis. So in heterogeneous catalysis, the catalyst, so let's just get the definition down first. The catalyst is in a different physical state or phase to the reactants. In heterogeneous catalysis, the catalyst is usually a solid. So the catalyst is usually a solid. So normally a metal or a metal oxide, usually on some sort of high surface area support. Okay, so lots of industrial processes involve heterogeneous catalysis. So lots of industrial processes take advantage or use heterogeneous catalysis. For example, 1. The contact process. So in the contact process, which makes sulfur trioxide, we use a vanadium oxide catalyst, V2O5. So vanadium in the +5 oxidation state. In the Haber process, very important industrial process, we use iron solid. Okay, so let's have a look at how a heterogeneous catalyst works. So the steps are relatively straightforward, and what we'll do is we'll try and draw a little cartoon explaining how this works. So the steps to remember. So the steps go as this. The first step is the reactants adsorb onto the catalyst surface. So the reactant adsorb onto catalyst surface. So adsorb, they just stick on the surface, okay? And as the concentration of the reactants increases, the reactants get closer together, and as they get closer together, there's a larger chance that these guys are going to come into contact and collide and react. And then some of the bonds in the reactant molecules weaken. And then let's think about what the last step is. So as some of the bonds in the reactant molecules weaken, there's a greater chance of making the reaction easier. And then what's going to happen next? So what happens next is once the reactant molecules have had their bonds weakened by adsorbing onto the catalyst surface, a reaction takes place. So we're going to say that some of the bonds in the reactant molecules weaken and the molecules react. And once they've reacted, they form products, and then the products are stuck on the catalyst surface, but then they desorb. And then the products formed desorb from the catalyst surface. And those are the 3 points that you have to remember for if you ever get a question, how does a catalyst work? Give the mechanism for how a catalyst works, I should say, because you could answer it through an energy profile diagram, but if it asks for the mechanism, then this is what you have to state. So that was heterogeneous catalysis. Now let's have a look at homogeneous catalysis. So in homogeneous catalysis, this is where we have the catalyst in the same phase as the reactants. So in homogeneous catalysis, the catalyst is in the same phase as the reactants. So most of these reactions involving homogeneous catalysts are going to take place in solution, either as aqueous solutions or in the liquid phase. So most of these reactions are solution based. Okay, so let's have a look at an example. And this is a classic example of where we have iodide ions reacting with peroxide disulfate ions. So I'll give you the overall equation first. So here are my iodide ions, 2I- plus my peroxide disulfate, which are S2O8, 2-, and these guys form I2 plus 2 lots of sulfate ions. Now, just looking at this, we can see quite clearly that the activation barrier to an iodide ion and a peroxide disulfate ion colliding is going to be high. And the reason for that is the iodide ion has a negative charge and the peroxide disulfate ion has a 2- charge. So bringing these two negative species into contact for a reaction to occur, because remember they need to collide for a reaction to occur. Look, there's going to be a huge activation barrier to this. Absolutely mega activation barrier to this, right? And what we do to overcome this is we use a catalyst, because remember these two negative species are going to repel, and that repulsion is going to be big, so therefore the activation barrier is going to be large. How do we overcome this? Well, we need a mediator. So what we do is we add a homogeneous catalysis in the form of Fe2+ slash Fe3+. And what we're going to look at how the Fe2+ overcomes this large activation barrier. Okay, so if we break this down into redox, redox half equations, it does make sense, okay? Because the iodide ions in this reaction, so the iodide ions, I'll just get rid of the Fe3+ for clarity. So the iodide ions are being oxidized and my peroxide disulfate ions are being reduced. Now, if we start with Fe2+, Fe2+ can be easily oxidized to Fe3+. I'm not going to give you the reduction potential for this, you just have to have a word for it. So what happens is my Fe2+ can be oxidized to Fe3+ plus an electron. Okay, so then if this is my oxidation reaction for the catalyst, let's couple it to the reduction reaction given in the question. So there's my peroxide disulfate, and I'm going to make 2 molecules of my sulfate ions, and this is a 2-electron reduction because that charge balances, so I need 2 electrons on the left hand side. So what I have to do to the oxidation reaction, so that's my reduction, just label it, I need to scale my reduction up by 2. And then what I'm going to do, I'm going to add these guys up. So now my electrons cancel out. And if I add this up, I will get 2 Fe2+ plus my peroxide disulfate goes to 2 lots of Fe3+ plus 2 lots of my sulfate ions. So that's great. I've generated my sulfate ions. But the problem here is now my catalyst is in the Fe3 plus state. And remember that catalysts don't get used up overall. They remain unchanged overall. So what we have to do is reform the Fe2 plus, because that's behaving like the catalyst. It's behaving like a catalyst because now we have a positive species and a negative species. So these guys can now come into contact, and there isn't going to be a large activation barrier because opposite charges attract, and they're more likely to collide and meet and produce some Fe3 plus and some sulfate ions. But then remember that the Fe3 plus needs to be converted back to Fe2 plus if it's a catalyst, right? So then what we do is we write our oxidation reaction for my iodide. So my 2I minus goes to I2 plus 2 electrons, and then I write the reduction for my catalyst. So my 2 Fe3 plus gains 2 electrons to form 2 lots of Fe2 plus. Okay, and then what I do, I add these guys up. Now, if I add these guys up, you'll see that my electrons cancel. So now it reacts with the iodide ions, and the iodide ions get oxidized and the Fe3 plus gets reduced, forming I2 and 2 lots of Fe2 plus. Okay, and that also is a favorable pathway because that's my negative species and that's my positive species, and these guys can react now. Okay, and then what we're going to do is we're going to have a look at, I'll label that as reaction number 1 and that is reaction number 2. And then what's going to happen is let's see if we have any like terms. Well, I've got an Fe3 plus on this side, on the left hand side, if I add 1 and 2 up, and an Fe3 plus on the right hand side. So those guys cancel out. The Fe2 plus in reaction number 1, and there's an Fe2 plus on the product side in reaction number 2, so those guys cancel out as well. Okay, so then if we add up 1 and 2, we should get the overall equation, and let's have a look. So if we add up 1 and 2, do we get the overall equation that we started with? Let's just double check. So I've got my I minus, so I'll write that down. So I've got 2I minus. Check. And then I've got then I've got the peroxidized sulfate. Tick, tick. And then I look at my products. I've got I2 and 2 lots of the sulfate ion. Tick and tick. And you can see that the catalyst doesn't appear in the chemical equation because it was used up. So the Fe2 plus was used up in the first part and then reformed in the second part. And this intermediate, which is Fe3 plus, was formed in the first part and then used up in the second part. So all the terms cancel out, and hopefully that makes sense and is helpful. So just want to say a big thank you for watching. Really helpful to support the channel, and if you like what you're watching, click that subscribe button and check this out for more videos coming your way. Ta-ta.